Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
It's a great pleasure to have Professor Kumar Murthy from University of Toronto, the chairman of Math Department and the Ganita Institute, and today he's going to talk about variants of Lehmer's conjecture.
Good. Thanks. Okay, thank you, Venki. Let me begin with some motivation to. No, I have this thing. So let me begin with some motivation. What this discussion is about. If I have an RSA modulus, so it's an integer n, which is a product of two primes, p and q. So the problem is, if I give you n to factor it, to find the p and q. Now it's a fact that if I can compute factoring n is equivalent to computing phi of n. Right? Because phi of n is p minus 1 times q minus 1. That's equal to n minus p plus q plus 1. So if I knew n and phi of n, then I know p plus q and I know p times q, so I can find p and q. Okay? So factoring an RSA modulus is equivalent to computing phi of n. Now you can make a similar kind of statement with other functions related to phi of n. True if phi is replaced by other classical functions. For example, sigma of n, which is the sum of the prime divisors. But the point is that sigma of n is a Fourier coefficient of an Eisenstein series. This is a Fourier coefficient of an Eisenstein series. And so this raises the question of the relationship between Fourier coefficients of modular forms and factoring. Okay, so general question about the relationship between factoring and computing Fourier coefficients of modular forms. So that's a sort of a theme that's behind our discussion today. It's about that. Now we're not yet at a stage, at least I haven't yet figured out how to make an algorithm out of this. In other words, to make an explicit relationship. However, maybe someday it will be possible to show that factoring is as hard as computing Fourier coefficients. Certainly, it seems to be suggestive of that. Okay. Now, connected to this is a problem of once we move from classical modular forms like Eisenstein series to cusp forms, there comes the issue of vanishing of these cusp forms. So it's very difficult for us if we're trying to use a Fourier coefficient to factor and the Fourier coefficient happens to be 0. So we have to worry about that. So consider the classical example of a cusp form. Is the Ramanujan delta function. So this is, if you like, we can write it as, if you don't like q, or let q, 1 minus q to the n to the 24, where q is e to the 2 pi I z. So the expansion of this is the definition of the Ramanujan tau function. Okay, so these tau n's are certain integers. Now, there are lots of interesting questions about these tau of n's, and in some sense you could say that the arithmetic study of modular forms started with Ramanujan's work on these Fourier coefficients. They had been studied analytically before, classically, but to realize that these actually have arithmetic information, yeah, both multiplicative and just the fact these are interesting integers, started with Ramanujan. But now there's some problems about this. First is Lehmer's conjecture, which is the conjecture that is referred to in the title of this talk. So Lehmer's conjecture is the following. Is that tau of p is never 0. Okay. This in fact this is equivalent to the following. This is equivalent to the following statement. To the statement that tau of n is never 0 for all n. And the reason for this is basically because tau is a multiplicative function. In other words, tau of mn is tau of m times tau of n if m and n are co-prime. And moreover, tau of prime powers can be computed by is equal to tau of what, p to the a minus 1 tau of p minus p to the 11 tau of p to the a minus 2. You can compute the tau on prime powers inductively once you know tau of p. So using these two things you can show that this is equivalent to this. Okay. This conjecture is still open. We don't know. This is still open. Okay. No. It's not known. However, it is known the following. It is known. What is known? Okay, it's a good point. What is known? The set of primes is density 0. Set of primes p less than or equal to x. The set of primes p such that tau of p is 0 has density 0. And more precisely, the number of primes up to x such that tau of p is 0 is of course little o of pi of x, but in fact it's o of x to the log x, I believe log x squared. Maybe we need to put in a log. Okay, so x over log x to the 2 minus epsilon is known. And if you assume Riemann hypothesis or generalized Riemann hypothesis, that is the Riemann hypothesis for all Dedekind zeta functions, then one can show that the number of primes up to x such that tau of p is 0 is O of x to the 4/5. Sorry, even better, x to the 3/4. Okay, so it's a. Now one might. No, the correct factor is 0. Pardon?
Using that assumption only.
Using what assumption? Generalized Riemann hypothesis?
That could be improved x.
So that's a good question. Okay, let's raise that question. What about other modular forms? Well, if I start, for example, with CM modular forms. So CM modular form means what? I have an imaginary quadratic field. And I take a Hecke character, psi. So Hecke character, means it's a character on group of fractional ideals of K. Then one can define if you like, I mean, one way of saying it is induction of psi from GL1 to GL2, or viewing psi as a GL1 automorphic form, or equivalently one can consider the form f of z, which is a sum over ideals A in integral ideals, psi of A e to the 2 pi I norm A z. That form, such a form is called a CM form, a form that arises in this way from a Hecke character of an imaginary quadratic field. Well, you see from this that if I were to rewrite this, you see here I have the norm of A. So if I were to rewrite this in terms of n, then I would have here the sum over A, ideals A, such that the norm of A equals n, psi of A times e to the 2 pi I n z. Well, in particular, if n is prime, if n is p, and p doesn't split in k, then this sum is 0, right, of the norms. Well, you can get it off the web too, I think, right? Okay, so you see here, from here, clearly if there is no ideal of norm p, in other words, another way of saying that is p doesn't split in k, then there is no Fourier coefficient. Fourier coefficient is 0. So that means a sub p of f, if you like, is 0. So that can happen. So Lehmer's conjecture is for tau, but from that we shouldn't deduce that for any modular form the Fourier coefficient will never vanish. It's not true. For CM forms, half the coefficients will be 0. That's one point. Second point is that even in the non-CM case, if I take an elliptic curve over the rationals, you might say, what does that have to do with modular forms? Of course, I can still define an a sub p of E, namely it's the number of points on E over fp. That's p plus 1 minus that, I guess. Okay, can still define that. And then we can define a sub p to the a sub p to the alpha for any alpha by using the same kind of formula, inductive formula that we wrote for tau. And we can define a sub n by multiplicativity. And then you have a form, at least a series.
Just make sure that the Hecke operators are properly acted.
Hecke operators will, at the moment you don't need anything about Hecke operators because you define these numbers.
But the definition of a to the p alpha will actually ensure that, right?
Exactly. It will be the same, it will mirror the recurrence relation satisfied by the Hecke operators. Well, this thing here, anyway, starting from an elliptic curve, is a cusp form of weight 2. Now, what does weight mean? We didn't define that yet, but let's ignore it for a moment, okay? This is a deep theorem, essentially due to Wiles, but with people who added things to it. By I don't mean added, meaning I mean they're pretty non-trivial things that had to be done on top of what Wiles did. So this is a cusp form. This is the Taniyama conjecture. That starting with an elliptic curve, if you form this thing, that you get a modular form, a cusp form. Now this weight 2 means at least in our context, you only need to understand by that the following: that a sub n is bounded by square root of n times a function here. So I'll put here number of divisors of n times square root of n. Okay, number of divisors of n times square root of n. In general, if I'm dealing with a form of weight k, the Fourier coefficient a sub n would be bounded by d of n times n to the k minus 1 over 2. Okay, so here's weight 2, so this is a root. In the case of Ramanujan, it is tau of n, exactly, n 11 halves. Okay? This is very important. I want to stress that weight 2 gives you this kind of bound. In particular, this is much smaller than n. Okay? Now here, of course, this is an integer in general. One can prove omega theorems to show that in fact it does hit this bigger size. So in general, tau of n will be much bigger than n. But why did I tell you this example in this context? Because when you have such a thing, one can show, it's Elke's theorem, that AP is 0 for infinitely many p. And here what Venki was saying is correct. Expected value, expected is that the number of primes up to x such that AP is 0 in this case should be asymptotic to constant times square root of x over log x. So here you expect infinitely many. We know there are infinitely many. We expect this many. This is not known. This method of Elke's, Ram tried to make it explicit, and the best lower bound is something like log x. Not even x to the epsilon is known. So therefore, with these two examples in mind, we should be aware that for modular forms it could happen that the Fourier coefficient does vanish. Okay? Just happens that for Lehmer is conjecturing that it doesn't happen for tau of n. Okay? Is that clear? Okay, good. Now let's look at a related problem. Is tau of p 0 mod p? So certainly if tau of p is 0, which Lehmer says should never happen, then it's divisible by p. But it's possible it's not 0, but it's still divisible by p. Now this does happen, and let's see if I can give you some numbers. Yes, it happens for for p equals 2. In fact, tau of 2 I believe is 24 or minus 24. So it happens for 2, it happens for 3, it happens for 5, and it happens for 7. Do you see a pattern?
All the prime numbers.
The next one is 2411. And that's, I think, those are the only ones that it's known.
What is the motivation of this question?
We'll come to that. No.
Okay.
We'll come to that.
2357.
So then you're stuck for the next one. Now the question is, what do we expect? Are there infinitely many of these? Nobody knows. So not known whether there are infinitely many. It's not even known. It's not known whether a density is 0. So neither an upper bound nor a lower bound is known. So it's not known if it is little o, if number of primes up to x such that tau of p is 0 mod p is little o of x, little o of pi of x.
It's a complex function that puts severe conditions, right?
Yes.
The particular condition.
What
Considered as a tau of p.
Yes.
It puts severe conditions on
Oh,
the
yes.
function. Yeah.
Oh yes, right. It has tremendous symmetry. But then the point is, how do you use that analytic property for this purely arithmetic statement? Okay, so we don't know that there are infinitely many. We don't know that they're rare. So the situation is a little bit like V for H primes.
Yeah.
is reminiscent of V for H primes. So here we're looking for primes such that 2 to the p minus 1 is 1 mod p squared. See, by Fermat you know it's 1 mod p, but does it happen that it's 1 mod p squared? You don't know they're infinitely many, you don't know that you can't get a good bound for the number. So that's the situation. Okay. Now Nikolai asked.
P to the power 5 or something, you can prove something?
No, I don't think so. I think if you assume ABC conjecture, you might be able to prove some large power doesn't happen. Yeah. Now let me see. Nikolai asked for some motivation. Why study this problem? Okay. Why do we care about this? Partly it's just a mathematician's interest in things they can't do.
It's also the case that if you're trying to compute, show, like you said, RSA problem, you need to know that it's not 0 mod p, because exactly how those cases will go bankrupt.
Yes, but yeah, so that's it. You're right. Actually, let me say, in that context, let me say a couple of things here. Why do we care about that? If we were dealing with a form of weight 2, with a form f of weight 2, rather than this form of weight 12, okay? So let's say f of z is summation a sub f of n e to the 2 pi I n z. And now I'm asking, and such that the a sub f's are arithmetic, so in other words, eigenform of Heck operators. And I'm asking you now about a sub f of p being 0 mod p, okay, instead of tau of p being 0 mod p. Well, if it's weight 2, you see a sub f of p, as I said, is bounded by 2 root p. So if you have a number which is bounded by 2 root p and is divisible by p, it's got to be 0. If p is at least 5, this implies that a sub f of p is 0. So we're back in the old problem we were talking about. If the weight is bigger than 2, of course, you get a bound like in the case of tau, it's just p to the 11 half. So it's quite possible that this can happen and tau of p is not 0. Okay?
So the good factoring method is tau of pq, he says tau of p equal to 0, but tau of q is not equal to 0.
Yes.
Mod p, then you can factor it.
Yes. I think the problem with those moduli is that, yeah, right, okay. Okay, and the second point, as I was about to say, is that it is just outside what known techniques can handle. So what do I mean by that? If I choose a prime L which is not P, and I ask how many primes are there such that tau of P is 0 mod L, see here the prime and the modulus are the same, tau of P is 0 mod P. Suppose I ask you tau of P is 0 mod L, then I can estimate it. This we can estimate as roughly 1 over L times pi of x for L sufficiently large. And we can make explicit what that means sufficiently large, and we can say what it means for small l's too, what the density is. Okay, that can be answered, and the tool that's used here is the Chebotarev density theorem. Okay, it's a theorem about equidistribution in number fields.
L is prime.
L is prime. Actually, this will work even if L were not prime. You won't get exactly 1 over L, you'll get a density which is proportional to 1 over L. Okay, so when L equals P, that whole method fails. Namely, the Galois representation, which gives rise to the number field to which you can apply the Chebotarev density theorem, yields no information, at least apparently, in the case where the modulus is equal. Okay? So those are two reasons for wanting to look at that problem. Okay. now, sorry. Okay, good. But now I can ask you, just as we observe that tau of p equals 0 was equivalent to saying tau of p not 0 is equivalent to saying tau of n is not 0, is there an n version of this? Okay, is there some version of this it involves n instead of p? So one way of saying it is, so the question is, what is the n version? Well, one way of thinking of this is to say that tau of n, since we're expecting that, so here we're expecting that the number of primes up to x such that tau of p is 0 mod p, or tau of p is not 0 mod p, should be, this should happen, this is what we expect, that being tau of p being divisible by p is rare. So not being this, we expect should be density 1. We don't have no way of proving that. So we might think that the n analog of this is to say that the number of n less than or equal to x such that tau of n and n are co-prime should be asymptotic to x. We may guess that purely in analogy with this, right? And this turns out to be provably false. So that's the theorem I would like to talk about. So this is false. Yeah, it is good. Exactly. It is good news. So which is what we prove. This is the theorem. F is a normalized eigenform. Weight k. Let's assume that suppose that the Fourier coefficients are rational integers. In general, they'll be integers in some number field. I'm assuming this for simplicity now, otherwise a little bit more complicated. Then the number of n's less than or equal to x such that n and a sub f of n are co-prime is bounded by x over log x.
Normalized means some kind of decay conditions.
No, normalized just means the first Fourier coefficient is 1. Yeah. So in particular, and that is, in other words, the number of n's to x such that n and af of n is not 1 is asymptotic to x. So that means if I give you a modular form and I pick an n at random, then most likely it will have a factor in common with the nth Fourier coefficient. Now again, let's say this again. I fix the f and I pick n at random, then n will have a factor in common with the nth Fourier coefficient. Now suppose this form, which is completely mine to choose, is of weight 2. Well, that's the point. In general, we don't want to factor random numbers. We want to factor given numbers. So, yes. So let me just say here, in particular, if note that if weight is 2, then a sub f of n is O of, look, n to the half plus epsilon. And this is telling me that this thing has a factor in common with a number of size n. So that's good. Okay. Now, before I go into I think rather than trying to prove this, let's see now, we might say, what do we need? But to use this for factorization, we actually need another version. So here's what we need, and if anyone here knows the trace formula well, maybe you can help me prove this. We need the following version: fix n, and now fix also level and weight. Okay, so consider a basis of forms of cusp forms of weight k and level n. Then the number of f's in a basis here, by this I mean basis, such that n and a sub f of n is not 1, show to me it's less than constant times the dimension of sk of n for some c less than 1. You see, I'm trying to, in practice, I want to factor little n. So if you can show me that as I vary over a basis of cusp forms of weight k, there's a positive proportion of them that will have a factor between the nth Fourier coefficient in common with the nth Fourier coefficient, that's good. Now I can pick an f at random from a basis, assuming I can compute the nth Fourier coefficient, then I can test the GCD. Testing GCD is very fast. And within a few number of steps, if this is according to how big this is, I'll be sure to get a factor. Yeah. Okay? So this is a kind of...
What can I implement a primal test for this?
Yeah, I'll tell you why yes and why no. But it seems to me that one has to use a trace formula of some kind to be able to prove this theorem, as opposed to the Chebutarov type of arguments that are used to prove this theorem. Okay? Perhaps.
What's the technical difference?
Well, I mean, in this case, the technical difference is I fixed one Galois representation because I fixed the form. Here, I can't use Galois representations, I think. Yeah. So probably needs trace formula methods. And of course,
You conjecture this to be true?
I think it's probably true. Yeah. I don't know, conjecture is probably very strong, but I would expect it to be true. Second thing is that what will this achieve? It will probably tell us that factorization and computing Fourier coefficients of modular forms are equally hard. Okay, at best, we can deduce from this that factoring is as hard as computing Fourier coefficients. Okay.
Why won't it give you a primality test?
Why won't it give you a primality test?
For example, small test little n is prime, big some capital n, do all this stuff. And you tried many times, maybe it tells you that n is
Yeah, actually, that's a good point. What about? Yeah, your point is quite good about primality testing, which is sort of complementary problem.
It's possible to say that
It's complementary to the. Yeah, yeah. Okay, so that's the big picture. Now we get into details. Eager for details?
yeah, but, I would like to. This actually is pretty exciting. So you know how to complete them?
No. Well, I mean, I don't have any new ideas on it. One standard method is modular symbols, and they're slow. Okay, so what's the technical tool that you use to study divisibility properties? Tool, main tool, as I already told you, is the pardon?
It's actually pretty interesting.
Yeah. Main tool is the Chebotarev density theorem. Okay. So I'll say something about the Chebotarev density theorem, and then what's the connection with how does Chebotarev density theorem arise? What's its connection to modular forms? Okay. I think that should be enough. Then there are a lot of technical calculations. I should also say that in the CM case, so we're going to get this bound on the number of coefficients, number of n's up to x, such that n and the nth Fourier coefficient are co-prime, is O of x over triple log x. We can ask, do you expect that to be best possible? I think in some cases, yes, we do expect it to be best possible. So it's little o of x, but just barely. Triple log grows extremely slowly, right? Okay. So the main tool is Chebotarev density theorem. So here's the situation with Chebotarev density theorem. I have number fields, extension of number fields. Let's say it's a Galois extension with group G. Then inside this Galois group, I can take a conjugacy class. Yeah.
That you expect to be holding good for every n, every capital N?
Yeah.
That's actually
Pretty strong.
no, that's actually pretty useful. You can actually go compute lots of stuff.
Yeah. So to tell you this, I don't have evidence. So if you know how to generate evidence for that, that's something that would be very interesting. What we need to do in Ganita, we've already started actually, with Kenneth has started, to understand how to compute Fourier coefficients quickly. So he's working with modular symbols.
Compute the basis functions.
Right, that's trace formula.
So isn't it by name? Pfizer did it, right?
Pfizer did some, right? And
Small n, it's easy, I think.
small n or n square free, capital N either small.
Capital is small is actually pretty easy.
Yeah, the difficulty comes when capital N starts getting divisible by high powers of primes. So if n is square free in general, also it might be easier. Then there's this Hijikata's version of the trace formula, which allows you to compute it.
For primal testing, you can choose capital N as you wish, right?
Yes, you can. You can.
Therefore, it should be-
Yeah. Yeah. Right.
Thank you.
So there's lots of possibility there. I mean, whether it is going to pan out or not, I don't know. But there's, in other words, just like when you go, how did people advertise elliptic curves once? That there's only one finite field of size p, but there are many elliptic curves over the same finite field. So that variability is what gives you an extra degree of freedom. So similarly here, you've got many levels, many weights, and many modular forms. Okay. So I'll be happy if anybody helps me with this trace formula.
I'm signed up.
Okay, good. Great.
I understand this question quite easily now. Modular symbols also, I know.
Very good.
Yes, a couple of examples. Some people actually gave talks here.
Okay.
Students.
Good.
I understand how to compute them, not completely, but by choosing capital N properly, I think you may be able to attack this problem.
Great. Okay. It's very good. So very fruitful trip. Okay, then I'll just quickly tell you the two things here. One that you need to know about how you prove these theorems. One is Chebotarev density theorem, and the other is Galois representations associated to modular form. It's not clear that either of these tools will help you in this version, but still it's good to know them properly. Okay, so here I have a Galois extension of number fields, and I take a conjugacy class. Then to each prime ideal of K, I can associate a conjugacy class, which we might denote Frobenius P, conjugacy class. You know this, right? Yeah? Okay, and now we can ask for the number of primes up to x, number of primes such that norm P, norm from where to where, K to Q of P is less than or equal to x, and Frobenius P is C. Okay, so Chebotarev gives us an explicit version of this. It's asymptotic to the density. So if you give G the discrete measure, then this C has volume C over G times Li of x, logarithmic integral of x, plus O of what? If you assume Riemann hypothesis, of course, you get an interesting something like x to the half times stuff, which, by the way, that's in this case, it's the stuff that's interesting. You know, it's x to the half times stuff. It's that stuff that's extremely important, and we don't understand that stuff yet. The x to the half, of course, comes from the Riemann hypothesis that the zeros are on the half line, but what else goes beside x to the half is not well understood.
So what do you mean by the most important stuff?
Well, I mean, if you assume Riemann hypothesis, you get here x to the half times the size of the conjugacy class times some other smaller things, log m x, okay, whatever m is. Now the point is, you may say, well, what's wrong with that? That looks pretty good. This is like x over log x. This is like x to the half. What more could you want? What more I would want is, I'm worried about this. I'll give you an example. What does it do for you? Okay. So this is an aside. If you look at this bound and I ask you now, find prime ideal of least norm such that the Frobenius is this given conjugacy class. You know, that's not an unreasonable problem, because if I'm from a computational point of view, you know, I know that every conjugacy class is hit, and I say, give me a prime. So I have to know how much I need to check. So I might say, well, firstly, I can make this implicit constant completely explicit, and then I will just see when does this dominate this, then I'm done, right? But the point is, so I ask, when is this thing bigger than x to the half c log mx? Well, the c's cancel, so this is about x over log x, so I get x to the half is bigger than log x squared log m times g, roughly speaking. I've abused notation a little bit. So this is telling me this thing should be squared. And you might ask, what is this log doing here? Well, that comes out to be a log, maybe a log g squared. So what's wrong with that? Well, what's wrong is that in the general group, if the group is not abelian, conjugacy classes are of different sizes. Yeah? If a group is abelian, every conjugacy class is a singleton. But in a non-abelian group, there might be the conjugacy class of the identity, which is a singleton. There might be other conjugacy classes that are huge. Now, if you think of primes as being randomly distributed, okay, and here's my group, and I'm throwing the primes. By throwing means I'm associating the Frobenius conjugacy class. Okay, so which area don't you think that if I have a big conjugacy class, it would be easier to hit it? Right? It's easier. It doesn't appear there. The conjugacy class has disappeared. You understand, Nikolai, the intuition? The group is divided into conjugacy class, and I'm throwing primes into them. If the conjugacy class is big, the likelihood of my hitting it is bigger. So I should get a bound for the norm of the least norm of such a prime, which depends on the size of the class, and it isn't here. What does that tell you? It tells you this is not the right thing. It should be something better than this. That's what I mean by important stuff.
Okay.
Exactly. If you
try to estimate this, okay, got it.
Right. So this is with Riemann hypothesis, and if you assume Artin's conjecture, in fact, you get the square root here.
Then C will be there.
Yes, then C will be there. But it's not even clear that's best possible. So there's a whole genre of problems on the Chebytarov density theorem that is completely open. Not even there are no theorems one way, there are no omega theorems either. In other words, that you cannot do better than this. Examples, we're missing those. So a lot of open problems here. But that's one tool. And the second tool that one uses is second tool is the Galois representation. So I have rho Galois Q bar over Q into GL2. Actually, the only thing I need to use here is Z mod L. So there exists such a representation. The property that it has the following property that if P doesn't divide L or N being the level, then Frobenius of P, which is a conjugacy class in here, rho sub F of that is a 2 by 2 matrix. So matrices have characteristic polynomial. This has characteristic polynomial T squared minus A of P mod L T plus P to the K minus 1 mod L. K minus 1, weight K.
Yeah.
F level N, weight K. So this means that this is what connects modular forms with Chabatarov. Because you see, this is a finite group. So that means this factors through a finite quotient. So that means there's some extension field, K sub L of Q, whose Galois group is the image of rho F. It depends on L. Right? And you can show if F in general for L sufficiently large and F not of CM type, this thing is essentially the whole thing. Not quite. Pretty much that this map is onto. Almost. So therefore inside here, if I take not a conjugacy class but a union of conjugacy classes, namely matrices of trace 0, okay, that's not a single conjugacy class. The conjugacy class in matrices are determined by Jordan-Holder theorem, by Jordan canonical form, determined by almost determined by the characteristic polynomial. Right? Not quite, but in a 2 by 2 matrices, there'll be at most 2 conjugacy classes if I give you the characteristic polynomial. Here I'm saying the matrix has trace 0, which means AF of P is 0 mod L. Okay, so but that's a condition which is stable under conjugacy. So I can apply Chabatarov to that. So therefore, using Chabatarov for this extension, we can estimate the number of primes up to x such that AF of P is 0 mod L. Okay, and notice I had to restrict here. Yeah, I cannot. This method will not work for studying AF of P being divisible by P. Okay, so this gives you whatever it is. It's 1 over L pi of x, Li of x. So using these two tools and some sieving methods, one proves the main theorem. And as I said, if you want to do this with the variant that I'm asking, I don't think these are the tools. I think the trace formula is the tool.
What do you mean by that?
Well, so yeah, sure. So the point is here, what makes this work? I have a fixed form, so I get one representation, and then I'm looking at primes varying. Okay, the Chabatarov works well for that. But now, if I fix the prime and I'm varying the form, Chabatarov is not the right tool. I need some other tool. The only tool I know that enables you to use all modular forms at once is the trace formula. Or maybe he does p-adic representations. I don't know. So I think there's lots of work to be done on this problem, and the applications will be nice. Okay? Good. I think that's all I want to say.
Thank you very much, and I'll tell